So gas stoichiometry just means that I can use gas laws as an input or an output into the mole bridge. Remember, the core of stoichiometry is using the mole ratio. I'm always going from quantity of one thing to quantity of another thing. So I have some amount of a reactant and I want to find an amount of a product, or I have some amount of a reactant and I want to find another amount of a reactant. And so what we can do is we can use gas laws. If I have pressure, volume, temperature, I can use gas laws. So over here, if I have pressure, volume, temperature of the first case, or the initial thing, I can find the moles using gas law, right? And then once I have the moles of that, I can find the moles of the other thing using the mole ratio. And then using the gas law and the moles that I found of the other thing, I can find gas properties. Or I could have other inputs. So there's kind of two cases for this. Let's call case one. Case one, I think of it as an easier case or a shortcut. Whenever you see the words STP, STP is an acronym. It stands for standard, temperature, and pressure. Let's do case two, which is not at STP. And so if I'm not at STP, then I'm going to use the other three quantities of pressure, volume, and temperature to find moles using the ideal gas law. That could be my input, and then I would use the mole ratio to find the other quantity, or gas law could be my output. Once I've found moles of the second thing, I could use two other quantities plus the moles to find pressure, volume, or temperature. Usually what's interesting is to find the volume, because the volume is a quantity. Okay, so let's do a word problem for case two, not at STP. So when 4.0 times 10 to the 7 liters of hydrogen at 503 degrees Celsius and 155 atmospheres react with excess of nitrogen, what is the maximum volume of ammonia that can be formed at 20.6 degrees Celsius and 1.007 atmospheres? Okay, so there's a lot of numbers flying around here. So one of the things I want to do is, like, they're giving me values for hydrogen. They're giving me values for nitrogen. Also, I want to have a balanced equation. This is actually the Haber process. It's a very famous chemical reaction. But we have a balanced equation, and I'm going to isolate. What's the information they gave me about hydrogen? So the hydrogen was at a pressure of 155 atmospheres. And the volume of the hydrogen was 4.0 times 10 to the 7 liters. So this is an industrial process. That's, what is that, 40 million liters of gas. So that's like a giant tank, right? And the temperature of the gas was 503 degrees Celsius, right? While we're at it, since we're trying to find the ammonia, which is the NH3, the information about that is different. The pressure is 1.007 atmospheres. So once we form the ammonia, the pressure gets cranked down in this ammonia making machine, whatever it is, right? And my temperature also goes down quite a bit. Actually, that's a little on the cool side, 20.6 degrees Celsius from where we were, which was really hot. And they want to, what is the maximum volume? So volume is my goal, yeah? Okay, so I have a balanced equation. The next thing I'm going to do is find moles of the known. Which one's my known here, by the way? I'd say it's the hydrogen, because I have 3 properties, whereas the ammonia is missing some stuff. So I'm going to find moles of the known, and so moles is equal to PV over RT. The pressure and the volume are okay, but what do I have to do? The temperature. I better change it to Kelvin. So I'm going to add 273.15, and That's pretty hot. That's 776.15 Kelvin. Okay. So I'm going to plug, now I could plug all those in directly. So that's going to be equal to pressure, 155 atmospheres, times volume, huge volume, 4.0 times 10 to the 7 liters, divided by gas constant, 0.08205 liters times atmospheres over moles times Kelvin, times temperature, 776.15 Kelvin, accurate to the ones place. So it looks like I have 2 sig figs because of the volume, but I get, that's a lot of moles. Well, we had a very large amount and a very high pressure. So that sounds reasonable. I got 9.7 times 10 to the 7 moles of hydrogen. Okay? So the next thing I want to do is find moles of the unknown. And so for that, I'm going to take the 9.7 times 10 to the 7 moles of hydrogen. And then the mole ratio is, let's go back to the balanced equation, is 3 to 2, right? So 3 moles of hydrogen on the bottom, 2 moles of ammonia equals just a little bit less. And also 2 sig figs would be 6.5 times 10 to the 7 moles of NH3. I'm still leaving my calculator values unrounded. And then finally, I want to find, this one's a long problem, find the volume of the unknown. And so, and I'm not at STP. If I look at the, I'm not in the, near it, but I'm not at 0 degrees Celsius, and I'm not quite 1 atmosphere. So for the ammonia, volume is equal to nRT over P. This is rearranging PV equals nRT to solve for volume. And I'm going to plug in everything I have. Oh, before I do that, look at the temperature's not right. I want to add 273.15, and that would give me 293.75 Kelvin, and this would be accurate to the tenths place. Okay, now I can plug everything in. So I'm going to plug in the moles, 6.5 times 10 to the 7 moles of ammonia, times the gas constant, 0.08205 liters times atmospheres over moles times Kelvin, times the temperature. The new temperature is now 293.75 Kelvin, divided by the pressure of 1.007 atmospheres. And I get, it's a lot, it's a big volume. The volume is equal to, but only 2 sig figs, 1.6 times 10 to the 9 liters of ammonia. Okay, so that's an industrial process to make ammonia. That's about as hard as they could get for gas stoichiometry. So I had to input the ideal gas law for step 1, and I had to output the ideal gas law for step 3, right? I always have to use the mole ratio.